All right, so in the last video, I essentially just went over the relationships between position, velocity, and time graphs, look at position, velocity, and acceleration graphs all with respect to time, give a little intuition on what acceleration looks like, and how all these things are related to each other. And also made a note on the importance of keeping yourself oriented correctly and making sure all of your negatives are in check with how you're setting yourself up, because a lot of the time there's more than one way to go about doing something. That's a case a lot of the time with these physics type problems. There are multiple ways you can get your answer. So with that in mind, let's get started at deriving some equations we can use to look at these relationships. All right, so let's say we have some system that's under some constant acceleration a. Constant a, and that is in meters per second squared. Well, we know that a equals dv dt. It's the change in velocity with respect to time. It's how fast your velocity is increasing or decreasing. It's your acceleration is the slope of your velocity graph. Well, let's do some rearranging here. We get dv equals a dt. Well, all right. Well, we know that velocity is the derivative. No, just kidding. We know that acceleration is the derivative of velocity. And logically, it follows that velocity we can find by integrating our acceleration. So let's do that. Okay. Now, a is just a constant. And so a is not a function of t, which means that we can just move it out front here. And we'll end up with the integral of dv equals a times the integral of dt. And then finally, we can get v equals a t, since there's a 1 there that's just kind of invisible since we factored the a out, at plus c. Now, the c is some constant. We don't know what it is yet, but we're going to go find that out. And so in the past, we've just plugged this in by, finding different values for these things at different times. Hopefully you'll see what I mean in a second. So let's say we have some system where at time equals 0, the velocity equals 0. So the velocity equals 0 at, hold on, let me make sure I'm doing this correctly. Okay, how about this? At time equals, well, no. Is that going to be anything I want? I apologize. Yeah, there we go. Okay. At time equals 0, the velocity is some initial velocity. So at t equals 0, we're at our starting velocity. And we're going to call that v naught, v sub 0, or v naught. It's a British notation, but it's easier to say than v sub 0, so I like it. V naught equals a times 0 plus c. And then it follows that v naught is c, and so then we transform this equation into v of t equals at plus v naught, since c is the initial velocity. And it makes enough sense. It's like, if you start at 5 meters per second, then if you start at 5 meters per second and your acceleration is 10 meters per second squared. Five, and then v equals, well, at time equals 1, I'll do t equals 0 too. At time equals 0, you haven't had any chance to accelerate yet. And so you're still going 5 meters per second. Then after 1 second, you have the 5 meters per second you started with plus 10 more. And then here you have the 5 meters per second you started with, the 10 you gained in the first second, and then 10 more. So then you get 25. And the pattern continues, 35, 45 meters per second. And so it's something that's linear. But this initial velocity, that essentially just determines where you start on this graph. And so you could start here. You could do that. You could do that. And that point right there, that's your initial velocity. All right, so now we know that our velocity under a constant acceleration equals AT plus V naught. It's pretty satisfying. Now, we know that velocity is the change of position with respect to time. That's how we define velocity. So we'll do a little substituting here. dx dt equals AT plus V naught t. Sorry, plus V naught. Then dx equals AT plus V naught all dt. Then we have these differentials here, and that's just calling to be integrated. Integrate both sides. X equals 1/2 AT squared, just sticking a power onto the t and dividing by 2, and a is just a constant, so it can just sit there happily, plus V naught times t, since we need to add a t into there, plus some constant. Okay? So, and then our constant, in much the same fashion as the initial velocity, you can say that you start at some position x, at x sub 0. If you start at x sub 0, that means that you have t equals 0. If you plug in t for both of those, you end up with c equals x naught, x sub 0. And then so you can transform this equation, make it a slightly more sophisticated, and you get x of t, just showing that it's a function of t, equals 1/2 AT squared plus V naught t plus x naught. And so hopefully that equation is not a mystery anymore. And it's very evident that it just comes from twice integrating your acceleration with respect to time. And that's about it for these equations. So I think after this, I'll go ahead and make one more video that details how to go about using these equations in various ways now that we know them. So hopefully that was helpful.